Okay, I think I'm streaming now. Susan, you're there. David Campos, I see you also. Good, good. All right. Well, I am hopefully going to be streaming soon. Hopefully, this is going through. Welcome, guys. I got a little lecture here. Oh, wait a second. You're not hearing a thing. I can see that now. Hold on. There. Now maybe you're hearing things. All right. So let me know how this is going. I'm going to wait a little bit here. I got a few seconds. It seems to be kind of a big delay in the stream tonight. So I'm going to wait until I start to see comments on the live chat. I see Susan there, Susan and David. If you guys wouldn't mind. Okay, good. Now, if you could also tell me you can hear me and see me okay, I will get started. Okay, she says she sees me. Can you hear me? That's the important thing. Hello, hello. Just seeing if you can see me. Hello. All right. Can you hear me? I can hear you also on YouTube. Very good. Thank you, Susan. I was just waiting for confirmation because I didn't want to get going too far in here and just have you guys go, I can't hear you, Tony. So okay. Good. Well, this will be the first and what I hope is a regular series of us kind of getting together and talking about whatever topic we're interested in. This took me quite a while to set up, so but I haven't rehearsed it yet, so you're going to see a lot of live glitches. But what I'm going to do is record this. In fact, I'm going to press record now. I am now recording this locally. Hi, David. And then I'm going to get started with the little lecture. It might take 10 or maybe 15 minutes. Then I'm going to stop recording, and then I don't know. We'll see how this goes. But anyway, this one is on dark matter. So I created this here, and hopefully my visuals will show up and things like that. But anyway, let's go ahead and get going. So the idea is to talk a little bit about what dark matter is and what our current state of knowledge is on dark matter, just very briefly. Like I said, about 15 minutes. Okay, let me get started. Hello, everybody. My name is Tony Darnell, and today we're going to talk about dark matter and our current state of knowledge and research regarding this very elusive particle. The idea of dark matter started a long time ago in the early 1930s. The American astronomer Fritz Zwicky was studying the movement of a handful of galaxies in the Coma cluster, which is a collection of about 1,000 galaxies, which is approximately 320 million light years from Earth. Now, using data published by Edwin Hubble, Zwicky calculated the mass of the entire galaxy cluster, the entire Coma cluster, and when he did that, Zwicky noticed something odd about the velocity dispersion, and this is the statistical distribution of the speeds of a group of objects of the galaxies. And the velocity distribution was about 12 times higher than it should have been based on the amount of matter in the galaxies. So that was weird. And as you can imagine, this was very surprising to Zwicky, who wrote that if this could be confirmed, then we would get the surprising result that dark matter is present in much greater amounts than luminous matter. So he was the first to really talk about this. And this result and the idea of invisible matter was a radical idea back in Zwicky's time. And it really kind of still is today if you think about it. Only now we have much more evidence that it actually exists, and much of this came from Vera Rubin, which I'm sure you've heard of. She measured the galactic rotations in the 1860s, and the 1960s and the 1970s, and that put the existence of dark matter without any doubt. Okay, now let me just show you something. This is where are my rotation curves? Oh no, I don't have my rotation curves. Oh. Okay, I had two examples of rotation curves. Oh no, I'm sorry. I can show you this instead. Okay, so here is an example of what Vera Rubin saw. Now, the observations that she saw were that upper curve up there. This is, if you start at the center of a galaxy, and you can see the little galaxy down in the origin of the graph, then the further you go out from the center of the galaxy, the velocity of the stars actually increased. That's what she saw. But what you would expect, if only the material there that you could see was responsible for the mass of the galaxy, then you would see a curve in that dotted line below. So in other words, the stars farther from the edge of the galaxy would be slower because they're further away from the center of gravity in the center of the galaxy than the inner stars are. But here she didn't see that. She saw the top curve. The stars were actually going way, way faster than they should have been going if all there was the mass of the stars, the gas, and the dust in that galaxy. So this was what Vera Rubin saw. Now, excuse me. So she noticed that the galaxies weren't rotating properly. And if all that made up the galaxy was stars, gas, and dust, then we should see a galaxy that rotates in such a manner that the outer stars are going around the galaxy slower than the ones in the middle. I just repeated that because I ad-libbed that other part, but I actually wrote the part I just read. So this is live, folks. Okay, so here's a comparison. Okay, so I had a animation of two galaxies rotating, and one that had a lot of dark matter in it was going a lot faster than the one that didn't have dark matter, but my software wouldn't load that animation for some reason, so I can't show it to you right now. I just tried to load it. So imagine two disks. On the left side, one of them is spinning very fast, and on the right side, they're not spinning as fast. So the one on the right would have dark matter in it, and the one on the left would have dark matter because it's rotating faster, and the one on the right would not. So since we're seeing these weird galaxy rotations, that was the first clue that it was actually the nail in the coffin, if you want to listen to Sean Carroll about the existence of dark matter. Now, another thing that was another observational piece of evidence that showed us that dark matter actually exists, and so even though we don't know what dark matter is, there are other ways that we can tell it's there by looking at the way light is lensed around galaxy clusters. Now, what you're looking at here is the images of the frontier fields, which was taken with Hubble. And HST looked at six different galaxy clusters like this one for a long time and built up these kinds of images. Now, what you're seeing here is these elongated shapes. You could see an elongated shape up on the upper right of this image. That's a galaxy. That's a galaxy that's being smeared out by the gravitational lens of the galaxy cluster in front of it. And the galaxy cluster is the foreground cluster are these big yellow blobs that you see that are kind of circular or elliptical in shape. That's the foreground galaxy. And these little tiny galaxies all over the place are background galaxies. So by looking at the gravitational field of the galaxy cluster in the foreground, which in this case is Abell 370, and then looking at the distortions that are all around it from background galaxies, astronomers are able to build a model that described not just the visible matter in the galaxy cluster itself, but also showed the distribution of dark matter in the cluster as a whole. And there are many models showing where the dark matter was, and without using these models, they wouldn't have accurately been able to describe the lensing that Hubble saw. So clearly, the dark matter was there. Another big piece of observational evidence. Now, this is brand new, folks. This right here, this was just released late in 2018. And this is another observational clue that dark matter is real. This is the most accurate large-scale map of dark matter that we've made so far. It was done by the Dark Energy Survey that just completed observations. They just finished their survey. This map analyzed the shapes of 26 million galaxies using gravitational lensing. 26 million. And in the same way that the frontier fields predicted where the localized dark matter was around Abell 370, the Dark Energy Survey was able to measure that lensing of all those galaxies and apply models to see if the dark matter associated with the 26 million galaxies could be associated with small perturbations in the cosmic microwave background radiation, which was measured by the Planck Space Telescope. And it turns out, if you look at these black circles that are throughout, that are superimposed on the cosmic microwave map made by Planck, look at where all the dark matter is lying. It's lying in where you would expect. By the way, the dark matter map, or the Planck map, is a temperature map. Red is slightly hotter than the blue areas. And these are perturbations in the early universe. And the dark matter helped shape that pattern. And where the dark energy survey looked, of all of the millions of galaxies that were lensed, they're able to tell where the dark matter is. And as you can see, there's a lot of it clumping in the bright red areas. That's the higher temperature, and it is bringing the clumpiness to the early universe. So this supports the dark matter, dark energy theory of the universe. And so you may be asking, well, what is that theory of the dark matter and dark energy? Well, we've all seen the pie chart of, let me see if I can get this going. We've all seen this pie chart that shows the matter distribution in the universe, right? And based on Rubin's measurement and all the subsequent observations that followed, like the frontier fields using Hubble, the DES results, physicists now think that dark matter makes up about 27% of the stuff in the universe. Which is about 7 times more than the regular baryonic matter we're all familiar with. Baryonic matter is the atoms, the dust, the gas, and all the stuff that we can see, feel, and touch, and all that other stuff. So the burning question is, what's it made of? What is the stuff that makes up so much of the physical universe? And now, since Rubin's pioneering observations, a number of dark matter candidate particles have been proposed, but so far, all of them, we haven't found any. We've been looking by some of the world's most sensitive instruments. And part of the reason for this is that physicists aren't exactly sure what they're looking for. In fact, a small minority of physicists think that dark matter might not be a particle at all, and it's just an exotic gravitational effect. And this makes designing dark matter experiments kind of like finding a car key in a stadium parking lot and trying to figure out where the vehicle is that it goes with. So there's a pretty good chance the car is there somewhere in the parking lot, but you're going to have to try a lot of doors before you find your ride, even if it even exists. So I'll play a clip from Sean Carroll in just a minute that kind of highlights this. So, among the candidates for dark matter particles, or for dark matter, are subatomic particles with goofy names like axions, neutrinos, massive astrophysical compact halo objects, which are called machos, and weakly interacting massive particles, or WIMPs. Now, if dark matter is a particle, then how can we find it? Well, there are several observatories trying to find out. One is DarkSide. Hang on, let me see if I can show it to you. Where is it here? There's DarkSide. And let me see if I can bring it up. There, that's DarkSide right there. It's located deep underground in Italy. And DarkSide is essentially a large tank filled with liquid argon and equipped with incredibly sensitive sensors. Now, if WIMPs exist, weakly interactive massive particles, then physicists expect to detect them from the ionization produced through their collision with argon nuclei. They'll make a little flash of light. And another observatory is called SABRE. And here's a picture of SABRE. It's not that great really, but it's all I have right now. Which will also look for direct evidence of dark matter particles based on the light produced when energy is released through their collision with a sodium iodine crystal. Now, SABRE has been running since 1995 and was used to look for solar neutrinos, but now it's looking for dark matter. Now, so far, no one has found any particle that could be called dark matter. So people are looking. Now, some scientists, a small minority now, think that dark matter might not be a particle at all. Rather, it's an exotic gravitational effect that extends to the large-scale structure of the universe. These astronomers think that there should be a modified version of gravity, which they're calling MOND, which stands for Modified Newtonian Dynamics or something like that. And they say that that might explain the gravitational lensing effects and the galaxy rotations that we see throughout the universe. So with that, I'm going to put a clip up. Hopefully this will show, and you'll be able to hear it. And this clip came from the Ultima Thule live stream that Christian Reddy and I did back over New Year's Eve. And Sean Carroll showed up, and I asked him this question about dark matter, finding dark matter versus MOND. And here is what he said.
Well, do we have one more question?
Well, I do. I have a question for Sean.
I bet you do, Tony.
Yes. So Sean, I there's so much I'd like to talk to you about, but I just want to get your impression of what do you think about the? Are you discouraged at all about this search for dark matter particles? But I guess you're right in the sense that this does take a long time. Or do you think these modified gravity folks are starting to gain a little bit of traction? For those of you who don't know, there's a debate going about the rotation. What we see in the universe is the visible matter in the universe. We can infer the way it's behaving is not behaving the way it would if it was just the matter that we could see interacting with it. So we infer the existence of something we can't see, like dark matter, to explain things like rotation rates of galaxies. We've been looking for that dark matter particle. We haven't found it yet. But there are people who think, well, wait a minute, maybe there's something about gravity on really, really large scales we just don't understand. And Sean, I just wanted to get your thoughts on that. Are you discouraged? Is this to be expected? I mean, what is your opinion? I know that this is speculation.
Yeah, I mean, there's two separate things going on. One is the possibility of modified gravity, which is always a possibility. Any theory, in this case, Einstein's general relativity, could be not exactly right on some scales that we only learn about once our knowledge gets better and our experiments become more clear. However, there's essentially no chance that dark matter is not there. Modified gravity can't replace the dark matter, and the reason is because of the cosmic microwave background. It's a slightly complicated argument,
right?
But people made predictions ahead of time for what you would see in the microwave background if gravity were modified versus what you would see in dark matter, and then we did the experiment and the dark matter wins. So that's sort of an open and shut case. You can have both dark matter and modified gravity, but you can't have just modified gravity all by itself. Now, there's still the question why we haven't seen it, and that's a very good question. You know, it's not as if we should have seen it by now with a 99% probability and haven't, right? There was one particular model of dark matter, the weakly interacting massive particle, where probably if you had sort of asked someone in the year 2000, they would have said, given what we're able to look at now here in 2018, the very end of 2018, we probably should have seen it. Right? 50, 60, 70% chance. But there's still plenty of room for it just not to have been seen yet. However, there's also the disturbing fact that we haven't seen any new particles at the Large Hadron Collider other than the Higgs boson, which is part of the Standard Model all along. So I think that a lot of physicists had, including myself, had this expectation that there were a bunch of new particles at the electroweak scale, as we call it, near where the Higgs boson is in mass. And those particles, among other things, would explain the dark matter. One of them would be the dark matter candidate. And so we haven't seen any of these particles at all. So that expectation seems to have been wrong. And that means, it doesn't mean that dark matter doesn't exist. It means that we have to go back to the drawing board in terms of our expectations for what kind of dark matter, what kind of particle the dark matter might be. There's plenty of other particles that it could be. It could be axions or massive neutrinos or weird things that we can't even describe quite yet. But we should spend more time looking for those things, not just for weakly interacting massive particles.
Well, do we have one more question?
Well, I do. I have a question. Okay, so there you go. I think that concludes my little prepared talk that I had made, and I will push the stop button right now. I am no longer recording this now. It took about 15 minutes. That wasn't too bad, although I did screw up quite a bit of stuff. All right, so there's 4 of you out there. I see Susan Better and Better got there, and David Campos, and somebody else is probably there too. I didn't expect a lot of live viewers just because there's never a lot of live viewers for Patreon because it's hard to get a time when everybody can do this. But if you're watching live, let me know what you thought of that. Did it make any sense? Was it coherent already? Somebody had Susan, you had brought up the bullet cluster. I should have included that as well. That was another piece of observational evidence. These were two galaxy clusters that passed through each other and stirred up the dark matter in there. And by using again the lensing, they were able to make a dark matter map of the the surrounding galaxies, and that was another very important observation. I should have included that. That's true. But I like using the frontier fields, which is relatively recent, as well as the dark energy survey results. I thought those were really important. Probably going to have a hangout with. Well, I've got to hang out with them tomorrow, dark energy survey guys. But we're not going to talk about that. We're just going to talk about the dark energy survey as a whole. But I do want to bring them back and talk about some of the science that they're doing. So anyway, I just wanted to give you guys a brief update on our little chat on dark matter. I agree with Sean. I mean, how can you not agree with Sean Carroll? I mean, he knows everything there is to know about this stuff. But we know for sure that it's that dark matter must exist. And what's also very interesting about dark matter is that it doesn't interact with itself very well. So you can't get things like dark matter stars and things like that. So it's not only weakly interacting with us, it's weakly interacting with itself. So I think that's pretty interesting as well. Anyway, that's what I think we know about dark matter up to now. These observatories are still looking for the particle, but as Sean Carroll says, maybe it's not a WIMP, maybe it's something else. But we have to keep looking and keep trying. But it's almost certainly there. And for a long time that bothered me, but I guess I get it now. I mean, these just because I didn't like this idea of, well, there must be something there we can't see or interact with, but really the observational evidence is pretty overwhelming. So I don't know. So anyway, that's pretty much it. I guess I will go ahead and stop now unless you guys have any questions. If you're watching the VOD of this, the video on demand after this is over, I'll check, don't forget there's a Discord server. I check that all the time. There's one just for you. There's a channel just for you. And I look at that every day. So please feel free to use it. You should have a link to that in the Patreon account that you have set up. And anyway, look for a couple things to look for. This week I'm making the videos for a special offer for patrons who are at the $25 to $50 level. I am tearing down, where are we? I'm tearing down this bookcase, and I'm going to offer it to, at the $25 level, you'll get any book that I pick that I'll send to you, and I'll sign it from the bookshelf of Deep Astronomy. If you're at the $50 level, then you get to pick what you want. And you only have to join for 1 month, and then you can go back down if you have to. I mean, Patreon is so flexible that if you want it, you could do it. So I'm going to look on, I think early February, I'm going to look and I'm going to see which patrons are at these levels, and whichever they are, I'm going to reach out to them personally and say, you get the special offer. And if the following month, if you decide, well, okay, I got the special offer, I'm just going to go back to $1 or $5 or whatever it is you're doing, you can do that. I'm not going to make it be a long-term thing. But I'm trying to raise money for Deep Astronomy because I desperately need help. As anybody who's watched the live stream can see, I've got my hands full, and it would be great to have some help. And so I'm trying to raise some money in 2019 to get some help on this. And so I want to give things back to the Patreon community. You guys have given to me for years. Some of you who've been giving me for a really long time, you're just automatically going to get something if you want it. Some people they've given on the order of thousands of dollars. And so I want to thank them as well. So it's been a real ride. It's hopefully 2019 is going to be good. We'll be back next Monday. And, I guess we will come back. I guess live stream tomorrow. Telescope Talk Pro, 3:00. Dark Energy Survey. Hope you can make it on Thursday. Future in Space comes back with Harley. We're going to talk about in-space assembly with some people at NASA. Don't ask me how I guess they're just sitting around at home right now. So because of the shutdown, so they were eager to be on a hangout. So they'll be back on Thursday. So that'll be this week's schedule. All right, guys. Thank you. I hope you enjoyed this. Please let me know. You don't have to ask any questions, guys. This was just here. Just let me know if you like it. If you want me to do more of these. And if you got any other ideas of things you'd like to see or do together, then let me know. We'll do them. You guys are calling the shots. I'm trying to give back to you guys for what you're doing to support deep astronomy. So I want to give you things you want. All right. Talk to you later. I'm going to go ahead and stop the stream now. So I want to thank all of you for watching. And as always, keep looking up.